Alright, this is 4.3, problem number 6. We're looking at the first derivative test and the second derivative test and finding extrema, local extrema, absolute extrema, and then graphing what we found. So the first step is we've got this function f of x equals x squared plus 4x plus 6. We're only interested in this interval from -5 to infinity. And so the intervals are always going to have a little bit of a challenge compared to one that doesn't have an interval. If we're going from negative infinity to positive infinity, we don't have to check the endpoints for maxes and mins. But if we have an interval boundary that is a number, we do have to check that because it will either be a maximum or a minimum. So let's take a look though first and start with what we know, which is we're going to take the first derivative of f of x, 2x plus 4, in this specific case. Now remember, if we have a graph that looks like this, if the slope is equal to 0, we must be at an extreme point, whether it's a maximum or a minimum. So because the derivative represents slope, to find our extrema, we're going to set it equal to 0. So 0 equals 2x plus 4, and then we solve algebraically. 2x equals minus 4, which means that one of our extremas is x equals minus 2. So that's a critical point. Well, now we're curious, is it a maximum or a minimum? So to find out, we're going to go ahead and take the second derivative. F of x equals the derivative of 2x plus 4 is 2. And what the second derivative tells us is, for example, if we have a graph like this, the first derivative will tell us our critical points. The second derivative doesn't tell you the slope. It tells you the slope of the slope, or the rate of change of the slope. Now, if the slope is changing negatively, it's going to be concave down. If the slope is changing positively, it's going to be concave up. And you'll notice that if we have negative concavity, so the slope is changing down as we go from left to right, we're looking at a maximum. Whereas if we're looking at a negative if we have a negative concavity, we're looking at a maximum. And if we have a positive concavity, we're looking at a minimum. And our second derivative, when we plug in our point -2, so f prime prime of minus 2 is still just 2. And so we found that we have a positive concavity, which means that we're looking at a minimum. So now we know, using the second derivative, that this is a minimum. And I believe the problem, well, it starts with a maximum, so let's find the maximum. So the thing is if we know that x equals minus 2 is a minimum, so we're looking at a graph that starts at minus 5 and it goes to x equals minus 2, so we're starting at 5, minus 5, and we're going to minus 2. And we know that minus 2 is a minimum. And we know that there's no other maximums, local maximums. Therefore, and because this graph is always concavity up, because the second derivative is a positive number with no variable in it. So if we know it's positive the whole way and the slope keeps increasing from left to right, that must mean that minus 5, when compared to its surroundings, is a maximum. So the interval minus 5, when x equals minus 5, we're looking at a maximum. And we always have to test our intervals, so minus 5 is important to look at, because it will either be a maximum or a minimum. So now we've found one maximum and one minimum, and the problem wants us to find the ordered pair. And so what we'll do here is we're interested in, on the original graph, what our ordered pair is for our minimum. So we'll plug in our value -2 that we solved. It's a critical point. We're going to plug that into our original f of x graph. So f of minus 2 equals minus 2 squared plus 4 times minus 2 plus 6. And then we'll solve for that. Minus 2 squared is 4. 4 times minus 2 is minus 8, so minus 8 plus 4 plus 6, that gives us a value of 2. So we know that a minimum point is going to be when x is minus 2 And when we plug in minus 2 to our original function, we get a positive 2. So this is our minimum. This is our ordered pair of our minimum. And this is a local minimum. Now we're going to look at our maximum. So we're going to plug in f of minus 5, because we solved that to be a maximum because it's the interval. And because of the concavity, we know it has to be a maximum. So we're going to plug in minus 5 to our original f function, and we end up with minus 5 squared plus 4 times minus 5 plus 6. Negative 5 squared is 25. 4 times minus 5 is minus 20, so 25 minus 20 plus 6. 25 minus 20 plus 6 gives us 11. Let's see here. Alright, so what we've solved here is that when our value is minus 5, we get an output of 11. And this is our ordered pair for our local maximum. Alright, so now we know that we have a maximum. Let me write this in a little cleaner way. What we solved here is that our local maximum is this ordered pair. It's minus 5, 11 on the original function. And that our local minimum is negative 2 in the x and 2 in the y. Alright, so now we're going to start doing part C and graphing it, and that's going to help us find out if any of these are absolute extrema or absolute maxes or mins. So we know that this graph is a upward facing parabola because when we take the second derivative, it's always concavity up. We know that we have a local max at minus 5, 11. We'll say this is minus 5, 11, minus 5 in the x, 11 in the y. We know we have a local minimum at minus 2 in the x and 2 in the y. Now, if it's always concavity up, because the second derivative was always concave up, then we know that the slope must always be increasing. Not the value of the graph, the value of the slope must be increasing, so we're turning upwards the whole time. And so using that, we know that this side goes all the way to infinity. So there's no technical maxima or minima over there, because infinity isn't a real number, it's a concept. But we do know that we have a maximum here at our ordered pair minus 5, 11. Now to figure out if it's an absolute maximum, we need to look at the whole graph and see if there's any value larger than it. And if you'll notice when we look over here, there are indeed a multitude of values that are larger than 11. And so this is just a local max. But when we look at our minimum, which is at when x is minus 2 and y is 2, if we look everywhere else on the graph, there will be no point on this graph as low in the y direction as minus 2. So this is in fact an absolute minimum. And we kind of graphed it in solving this problem, so we'll say that we covered part C as well. It's important to use what we know about the first, second derivative to figure out kind of what the graph looks like. And once again, if there are no parameters, if it's from negative infinity to positive infinity, you don't have to worry about the endpoints. But if you have an endpoint that is a real number, that will always be either a maximum or a minimum, or perhaps a saddle point, but it's going to be one of those three, so it's important to check. As you can see here, the slope here isn't 0, and so it's not going to show up when we set the derivative equal to 0, so we need to set aside some extra work for figuring out what happens when x equals minus 5. I hope this was helpful, and I'll see you next video.